Welcome back to my channel. Today we will be discussing the coordinate system. The coordinate system, before coordinate system, uh, let's say for different units that contain and the elements, the geometry defined as or synthetic, synthetic to synthetic them, how we define the coordinate system. Yeah. Synthetic geometry used to have objects called primitives. Primitives can be lines, points, uh, any of objects, and like the lines, points, and then you can have subjects, something like that. And from these primitives, for these primitives, they have axes. These two constitute the significant in sense primitives can be anything, they need not be real. They need not be real. Medium. Thus, due to these primitives, I will not exactly axioms. Axioms take off the proven. These are often because of these they say, they used to say, they most famous, say, axioms like there are two laws. There are, but these two lines of objects, they cut at single point. The statement that the two lines cut at single point is the axiom. It is not true, not true, just true. So after that, we developed coordinate system. Coordinate system was uh, developed by the Descartes. Okay. After whose name they are called Cartesian. That is called Cartesian. The Cartesian comes from the Cartes of from the name of the Descartes. Is from this Cartes they got Cartesian. So, what exactly is Cartesian? Coordinate geometry. Coordinate geometry. Coordinate geometry uses basically points, but it describes the points. The exactly coordinate geometry is all about the position of points. Okay, these the position of the points is denoted by one or more number. So these are the coordinates, and there are called these numbers which denote the position are also or called coordinates. So what are the types of coordinates? Let's say in a single dimension, 1D, we have a number. This line, 0, positive 1, 2, 3, 4, 5, minus 2, so this is number line, right? A number line. On this, any of these positions, a point can be, like a point P can be anywhere here, like P. So what is P? The coordinate of P, just 3.5. P is equal to 3.5. That's it. But when it comes to 2D, we have, of course, two axes. X-axis, Y-axis. Right? Similarly, we have the axes are divided into numbers. One that we do and a y-axis. Then there's a point P here. The coordinates are indicated by the top perpendicular point here. That is this is maybe 7.5. That is now 7 levels. So this is 8%. Then it is denoted by 7 and 8. That's it. The two-dimensional coordinate system. The coordinate axis, the Euclidean, the Cartesian coordinates, the axes are at right angles. Let's say at right angles. So now, we can extend this to any number of dimensions. Dimensions. The same thing we can extend to the dimensions. We can you can go let's say there's a point here P. Then we can have x coordinate via this, and this is the z axis. So P will be denoted by x, y, z, or x, whatever the, let us say, the P can be, and one on x axis to y axis to z axis. So these are the values of. That is, this is a Euclidean space. Hidden. Now, yeah, depending on the direction, the coordinate axis can be right-handed, right-handed, axis, meaning it follows the its right-hand rule. Like you hold your thumb straight up, pointing finger going away from you, and the middle finger is parallel to you. These two fingers are closed. Good. So in this axis, this is the magnetic field, this is the electric field, this is the direction in which the conductor is moving in electricity. This is the right hand. So in this right hand rule, the direction of this object, the what do you call it, the conductor is anticlockwise. In the right hand rule, that is the right finger, which is the middle finger, and we have the thumb here. Then this direction is magnetic field. This direction is electric field, and the what do you call it? This is the direction of the conductor. Conductor will be moving in this direction, and the direction in which it moves is it goes on moving like that. So that is the anticlockwise. And the left hand coordinates, similarly, the left hand coordinates, you have the left hand here, your thumb is here, your that finger is here, and this is the middle finger, pointing finger, thumb. Then, of course, this is the magnetic. This is the magnetic field. This is the electric field. This is the direction. This will go in this direction, clockwise. In sense, this will go in. So that is the basically this is the left hand. It's instead of going this way in the anti-clockwise direction, this goes inside down from the top. That is the left. So the coordinates are also, we can simply say that these can be represented in same similar coordinates. These are the coordinates. X, Y, Z. Here also, same thing. X, Y, Z. And so this is X, Y, Z. Those are the right hand and left hand. These find application in electricity, magnetism, and of course, and everything related to electricity. And Fleming's rule, that is right hand release chemistry, electricity, related to Fleming's electricity, yeah, electricity. What's important here is the basically what is important here is the coordinate system. Okay. Now, apart from this Euclidean partition coordinate system, which is we have seen this one, which is made of axes which are mutually opposite in terms of 90 degrees. All three axes are at 90 degrees of each. And there are other coordinates also. Most famous of them, the most useful and most used are next to partition coordinates called polar coordinates. So, yeah. So what are polar coordinates? A point is chosen as this is called the pole, and from there a line is drawn with the length r. This is P. Next. So that's called it. The point is called equation is pole, and this ray, let's the difference between ray and the line is this is not ray. The other one. Okay? So the array is chosen here, and this is called pole, and this ray is called the polar axis. Polar axis. For a given angle, let us say, which are using here, you take a line from here, this is the polar axis, and the angle, the speed, the ray is making with the polar axis is called the is theta. Is theta. It is measured anti-clockwise from this axis. This is the polar axis, this is the polar axis, and this is the point. So this point is represented now as meaning these are the polar coordinates of this point. What are the polar coordinates? The constraints of the polar coordinates r is the distance from pole to that body, the length of the sphere, and the angle theta. The angle theta is measured from polar axis to the angle made by the sphere. To the sphere, let's say, the angle between polar axis and the sphere is called the theta, which is second exponent to polar. So, this r theta can also be represented as r theta plus theta. Why? Because once you go on turning this way, like this, and you reach theta, this theta is same as theta is equal to theta plus theta. So, this is angle equal to theta plus theta. And also you can again say minus or theta plus phi. Why? Because it's here theta. When you go here, what is happening if there is something like this? If in here, if this is R, this is minus R. Right? So you can always represent it as minus R theta plus phi. Those are the basics of um, those are the basics of polar. Whole itself is represented as 0. Because there is no range in it, is equal to arguments of 0. 0 is the length of the path. So naturally, first coordinate will be 0. And then to take that any theta is the any theta, it will be 0. So then and yeah, we go to the third, which one? Third coordinates. Third one is called cylindrical. Cylindrical coordinates. What are these cylindrical coordinates? Best, what you do is, this is something like this one. This is basically this side and this, that's the left side, this is the left. Here we are adding x, y, and z. So this is z. Z direction, this is x, this is y, and this x and apart from x and y, you have a point here, let us say P, then this x and y, let's say from here to here, is equal to z, get the contact is equal to, and So this is the starting about 320 or 50. Yeah, this is the experiment, this is the experiment, this is the experiment, and the angle is turned, let's say, from to here, here to here, the angle is turned is called theta. And just the z direction we have had it, and this is the written r theta z, let's say, this one. And the next one, fourth one, is spherical coordinates. The spherical coordinates, what they do is they take the cylindrical coordinates of r and z to they add this take coordinates r and z to rho and phi. They convert this into rho and phi. Meaning, here we have only r theta and z. They take this whole thing and add another phi to it. This rho is like r. This r is now rho. The phi is this entire thing, this whole cylindrical coordinate system, it took and added another angle phi, which makes it the spherical. And this triple will be now rho theta phi. But to me, it's a little confusing, complex. But once you understand the concept of these polar coordinates, r theta and r theta v, r theta v will be three-dimensional in the sense you have one circle left here, you have a circle. The circle you give it you go on lifting the circle. It's like, let's say it is elastic, it's made of elastic. You go on moving the circle, so it won't take it in. Right? So from circle to, if you go on lifting it this side, if this is elastic, then you can create a cylinder. So this is cylindrical coordinate. And this cylindrical coordinate, if I use another time, it becomes a spherical coordinate. So, yeah, anytime you don't, and then want to know more, you can contact me, you can put a comment, and I will do. This is sticky business. So we have finished everything. we are using the transformations. Let us say we will be data the use this way directly by this is data. So what will this be converted into digital? So naturally, change it particular here. This naturally this would be or something. What is the sample here? Sample is let us go to your website. Time data is PA by 40. PA of PA is equal to 40 seconds. That is half. Right? Similarly, this portion from here to here will be half. So, this is where it is. PA is equal to similarly, let us say, the first at the same time. That's the capacity by looping. So looping is nothing but R. So value is equal to R. So these are the you can either represent this in polar coordinates or this is this will be or cos theta or sin theta. Right? So even that way you can look at it. But that is basically we are changing the Cartesian coordinates into polar coordinates. If you know the numbers here, then we can also represent them in this way. That is the let's say if a transformation, we want to do a transformation, if the one dimension axis, really 1, 2, 3, 4, 4, that's fine. Then if the all these coordinates can be transformed into other coordinates. Here we exactly from Cartesian coordinates to polar coordinates. Here, if you want to shift this 0 to somewhere here, let's say, meaning now the new origin will be here. Meaning this will become 0 now. What will this be? This will be minus 4 then. Right? So let's say you can put the transmitted by touch coordinates. And next going further. Line handling, if there are, let us say, three coordinates, three coordinates here, let's say uh, this point P is 1 to 3, let's say. You want to keep this one same and change these two. What will happen? So this the one axis you the point value of one axis you keep constant. You change the other two. X is constant, Y and Z change. So it results in entirely a new curve called coordinate curve. That coordinate curve, if it is a straight line, let's say, this coordinate curve is a straight line, then it is called coordinate line. You can as well have orthogonal coordinate curves. Yeah. If let's say in XYZ X is constant, YZ are equal to 0, then this is called the coordinate axis. That see here this y component is not there, z component is not there, only x component is there, constant. Then what happens? This reduces to coordinate. Then and the same goes for three-dimensional objects also. What will happen with the three-dimensional objects? Um, in total coordinate system, if you hold the row, that is the equivalent of where right? That row, if you hold the row constant and the change the other things, then this will result in spheres with center at point. Right? Like rho is constant, rho is time constant, and it is surfaces. The surfaces it produces is very ornamental. This question, if you do rho will be constant and rho will be constant and they will be spheres. Spheres result with center at constant. The three-dimensional space two surfaces, two coordinate surfaces. Let us say there is a plane here. Let's see, let us take another uh, axis here. There is another plane here. So this intersection from here to here will be, if they are straight lines, that may be a straight line, but that will be a curve. The intersection of two coordinates, two coordinates will result in the intersection will be the. Similarly, coordinate we can have coordinate hypersurfaces are result of keeping one uh, coordinate constant of n-dimensional coordinate system. N-dimensional coordinate system. Meaning it has n, let's say it has 3, you have kept one dimensional constant, the other two dimensions, they are called coordinate hypersurfaces. Just to doesn't make much sense if you use 3 as a 4. Then if you get some get a coordinate of the it is. Now, in geographical coordinate systems, we are very familiar with the geographical coordinate systems, which are nothing but our longitudes and latitudes and longitudes of are the most familiar in practical. So there are three types of horizon. First one is the geographic coordinate system. Geographic system, which are nothing but longitudes and longitude and latitudes. The second variety is projected coordinate systems. Many of these what do you call when you create a small map yourself, right? whatever shape you land them to carry this side and then let us say it's Iceland, England, whatever. So when you creating a map, we say we mention generally we mention latitude. Instead of that, we can have them use different coordinate systems using numbers. The other one is geocentric system, which is nothing but, let's say, these days we see the earthquake map and all, they show. Right? There was a kind of this is the economy, representing Earth like a three-dimensional object, and they are used for the course GPS and etc. So those are the different types of coordinates that we generally use in daily life. So and today, uh, we will in the next class we will speak of that. So till then, thanks for watching.